Hey, everyone. Um, I think we're gonna look at linear algebra for today. Maybe we'll look at this diagonalizing matrix section. Worked examples. Okay, here we go. Damn, they got a lot. Um, let's think about number 3. Oh, I didn't clean up after myself last time I streamed. Ah, look at me, always leaving a mess. Hey, Rapture. There. Okay, so we have a matrix A with that diagonalization. What is the eigenvalue matrix for? It's asking what the capital lambda matrix is for A plus 2i. Oh, in the egg. Okay, well, it's a good question. I think I need to see. Do I need to see an example? No. Okay. What I need to see is I could just look it up, but let me get it myself. The relationship between um the eigenvalues and the determinant and trace. Now I want to look it up. Congrats, Joseph. Um, where would they talk about this? Yeah, it was just up there for the grabs. Oh wait, I don't remember seeing this in the lectures. Oh yeah, what's up, syntax? You won your appeal, your E&M midterm exam grade is now 100%? Oh, hell yeah, Joseph. Nice. Didn't you already do really well on that exam? But like I guess did you have to like debate one of your answers? 99%. Oh, okay. Hey, I mean from 99 to under that's something. Oh yeah, hey Slim. x inverse x and factorize, I'll give you the diagonal solution of a plus 2y. Oh, like writing is something like that, I guess, and then it might be easier to work with. I'm gonna think about syntax errors thing, but that's probably a better direction to go in than the way I was going. The brink of failing, yeah. Okay, so syntax, if R is an equivalence relation on set A, then every A in A is exactly one equivalence class. Hey, Star. Yeah, sure. Feel free to put it there in chat if you want. If R is an equivalence relation on set A. I need to look at what a couple of these terms mean again. So it's been a minute since I've done anything with this. Um, okay, starts asking a question just about factor and quadratic. If you don't mind syntax, I'm gonna do this one first because I think this is a little more direct, and then I'm gonna need to Google like the equivalence relation class thing again. Stars K is asking how to factor this. The 78 makes it kind of annoying. I always answer math questions, Harvey. Oh, I don't know if you see, but there's a game that's been like the flavor of the month called Schedule One, where it's literally like drug dealer simulator, and like, oh my god, that's the ultimate Donda's meth arc. The 15 in front also makes this annoying to factor. Oh yeah, meth is the greatest. Um, is there? So I normally when there's a leading coefficient that isn't one, I either try to factor it out, but that gives us some messy fractions if we factor it out. Like this fraction reduces a bit, but I don't really like it. Gonna play Minecraft. All right, I'll enjoy the meth. You enjoy your. I feel like Minecraft is worse than meth, but you go enjoy it. um, or actually, yeah, I think this will be the cleaner way of doing it. If I know the leading coefficient and constant term are both 15, that kind of limits our options for how this can look. Wow, wow. Mm-hmm. I said it. So in order to make a 15, we either need a 1 and a 15, or a 3 and a 5. Because like to make the 15x squared, and we also need a minus sign in here. I'm not dealing with the minus sign yet. I mean, what we instead of factoring out the minus 15, we can make our lives a little bit easier and factor out the minus sign. And then this problem is a little bit easier to think about because we don't have to worry about signs. So I'll put the minus sign out front here. And so now it's kind of like guess and check until they find the right answer. We also know the constant term is 15. So the same rules apply for what goes like here and here, here and here. It should be 1 and 15 or 3 and a 5. And I'm noticing that, no, I'm not noticing that. What's 15 times 5? Like if I had a 5 here and a 3 here, 15 times 5, that is 75, right? Yeah, I'm not crazy. So I'm thinking like 78 is 75 plus 3. And 75 is a multiple of 5. So that's what kind of led me to try and think of this. And so as I'm writing these out, I'm quickly like doing all this multiplication back out to check that it works. Like this is literally just guess and check here, but it does work. X times 15x is 15x squared. X times 3 is 3x plus 75x gives 78x, and then the 5 times 3 is the 15. Yeah, you could take a 3 out. It makes it a little bit easier. I don't know if it's the easy. I don't know if it makes it like that much easier, so I didn't bother. But you definitely can take a 3 out. So if this is, I mean, yeah, this is a little bit easier to work with. I could have done this too. But from here, I would do basically the same process as I did up here. Like, we have a -3 out front, and then just kind of fill in the blanks. So if we have a 5 there, we need to have a 5 and a 1. And in order to have a 5 here, we need to have a 5 and a 1 in some combination. In this case, I need to switch them around. And I know that because I need to get this 5x to be multiplied by that 5 to get us to 25, and 25 is just 1 away from 26. So that's how I would kind of do these problems. Okay, so let's go back to syntax. Equivalence relation has reflexivity. Right, I remember that. For equivalence relation. And then equivalence class. Oh, is that the set of everything that's equivalent to A, I guess? Hey, Fembucks. Okay. That's probably the key. If A is in multiple equivalent classes, then you have some issues with transitivity, right? Let me make sure I'm remembering equivalence class right. Equivalence class. Yes, okay, good. I am remembering it right. So I would say let A and A be in 2 equivalence classes B and C. Like I would just let A be in 2 and show a contradiction, I guess. Actually, what's Slim's saying? Oh shoot, I didn't shout you out, Slim. Let me do that. Academy uses ideas. aka Slim does a lot of streaming about pure math and financial math. Also makes YouTube videos. It's a cool stream. A and B, A and C. Okay, so you're going the same direction. Prove that B equals C. Yeah, so my argument is basically going to be that same idea. So, yeah, it's probably a better way of saying it than what I would come up with here. But the point is that if A is in multiple equivalence classes, then if you actually were to name this, like it's like it can't be in multiple equivalence classes and have transitivity unless it's the same class. Let B and C be an element of B and C respectively. Since A equals B and A equals C, by transitivity, B equals C. Oops. Dot, 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 dot. I guess also the symmetry part. Because by transitivity, I think the reason we need symmetry is we need these to form a chain. So if we want to actually use the transitivity, it'd be like we want to say B equals A and A equals C. So that way these A's are they're kind of like on the inside, and you could cut them out to say just B equals C. I think that's the symmetry part. Okay, yeah. Right. Yeah, thank you for the help with that, Slim. Okay. And thank you for the question, Syntax. Actually, I'll keep that up. I'll just shove it away. Be gone. Okay. Scrupulous horse. What does a binary do? Like, what do binary numbers do? Or you're talking about like a binary tree or something? Oh, okay. Okay, so as we talk, like just asking what binary numbers are, I did the classic me thing of asking a question, pausing, and then saying or something else, and then when I see yes, I don't know which one you're talking about. But I should be asking like, what is a binary number? I should say well, I guess what does binary do in computers? The way that we think about computers is we make basically like diagrams with the circuits. They're not really like they are circuits, but we're not thinking about like resistors or capacitors or anything like that. We're just thinking about the logic. I forget what the actual name of this type of diagram is, but you might like if you're building a CPU, it needs to be able to do certain things. You need to be able to store things. It needs to be able to do arithmetic. And you can build that up using what are called logic gates. And so you might have a logic gate that is an AND. It has two inputs. And if I was looking at the actual like what is a binary number in a second here. I'm just trying to explain why they're important. And it'll have one output. And what this gate in the middle here does is if you have electricity running through both of the inputs, only then will electricity run through the output. That's what it means to be an AND. If you have electricity in just one or in neither, then no electricity will come out of the output. And so that's just an example. There's logic gates with other behaviors like OR, NOR, NAND, a whole bunch of them. But the reason I want to give one example in particular is that it's kind of an all or nothing thing. Like either there is electricity running through that wire or there isn't. It's a binary relationship, 0 or 1, and no other options. And that's where binary numbers come up in computers, because it's a natural representation of that idea. And so if you write code for the computer, we write it in something resembling English, but the job of the compiler and all that stuff is to translate it literally into zeros and ones, and those zeros and ones get translated into, you know, this one means electricity does go in the input in some part of the CPU. This 0 means it doesn't go in the input in some other part of the CPU. And what a binary number actually is a number in base 2. We commonly, we have 10 fingers. Wait, there we go. And so we humans tend to think about things in base 10. And so you probably, it's common to learn in like grade school that there's a ones place, a tens place, a 100s place, a thousands place, and so on. And if you want to include decimals, we have a tenths, a hundredths, thousandths, and so on in the other direction too. And we can think about these as representing powers of 10. The ones place is 10 to the 0. The ones place is 10 to the 1. The hundreds place is 10 to the 2, 10 to the 3, so on, ... And then we also have 10 to the -1, 10 to -2, 10 to -3, and so on. And so the number 341.81 can be written as 3 is in the hundreds place, so 3 times 100, plus 4 is in the tens place, so 4 times 10, plus 1 is just in the ones place, so I'll leave that one alone, plus 8 times 10 to the -1, plus 1 times 10 to the -2. And I should say 100 is 10 squared. I'm kind of like mixing things, but 10 squared, 10 to the 1, technically 10 to the 0. I should be consistent about that. A binary number, if this is base 10, a binary number is base 2. So we still have a ones place, because 2 to the 0 is 1. But now we have a 2's place, a 4's place, or 2 squared, an 8's place, and so on. Same with the decimals. -1, -2, -3. And if you're working in base 2, well, I should say in base 10, we have digits 0 through 9. It's 1 less than your base. In base 2, we have digits 0 through 1. In base 3, we'd have 0 through 2. In base 100, we have 0 through 99. And so if we write the number 1010.101, we could do the exact, we could convert it into a base 10 number by using this exact same pattern up here. So this is 2 to the 1, 2, 3. Okay. So this one right here is in the 8th place. So 1 times 2 to the... Oh my gosh! I wrote 8 there. I meant to write 3 there. 1 times 2 cubed. 0 times... Oops. 2 squared. 1 times 2 to the 1. 0 times 2 to the 0. Running out of room. 1 times 2 to the minus 1. Plus 0 times 2 to the minus 2. I'm running out of room further. Plus 1 times 2 to the minus 3. And so then you can just do this math, and out pops a base 10 number. It'll be 8 plus 2 plus 1/2. I should use decimals. No, I shouldn't. Plus 1/2. Plus 1/8. I promise I know what to do math. I really don't. 5/8. So 85 over 8. Oops, not plus, equal. And that's, I don't know, use a calculator to find the decimal there, but I know what it is, right? It's 10 point something. It's 10.625? That's my bet. I don't feel like verifying it, but it's something like that. And so that's the basic explanation of what a binary number is. You could do the exact same exercise with any base you want. You could even have base pi or some irrational number if you wanted to go crazy. Negative numbers, I'm not sure those work. Imaginary numbers, I can't imagine those work. But like positive real numbers, as far as I know, all work. And you can do arithmetic with binary numbers just as well as you can do arithmetic with base 10 numbers. And base 10 numbers are something called decimal. Because deci is 10. And I guess with computer science, base 16 comes up a lot, and base 8 comes up sometimes. And it's kind of a funny thing with like bases higher than 10 because we need to invent new digits because each digit, it represents a number 0 through 15, but we only have digits 0 through 9, so that's why in hex they start to use letters. So A is 10, B is 11, all the way through F for 15. But yeah, it's kind of like maybe the basic explanation of what a binary number is and why it's important for computers. Let me know if that kind of answered your question, or if you want me to go in another direction with that, or anything. Hey, 6767, welcome in. Mostly hear from you. I'm going to shift back up to linear algebra, but let me know, Famished, if you do anything else. Um, So Slim's idea for this one before was to write I as x inverse x and factorize. That's true. Yeah, I should be any matrix times its inverse. I'm not seeing the or factorize what? I guess like just think about a plus 2 x inverse x. Oh, and then I guess we take, oh, maybe this is it. And maybe we want xx inverse. I'm not sure. We can always flip the orders of these if we want. I'm not sure which one is better, but if we know a is equal to this, let's sub that in. And I guess we can, from the left, factor out the x. And from the right, factor out the x inverse. So lambda plus 2i. Ah! Neat. So if you add to the, basically to the trace of a matrix, or if you add 2i, you just add 2 to the eigenvalues also, is what this is saying. The eigenvectors stay the same. Hey, Henrik, how's it going? Good to see you again. I'm so curious to see the whatchamacallit. 67, do you don't mind keeping it to English? I can't really read that. I'm good. I'm doing good too. Thanks for asking. I just want to see the expression for like characteristic polynomial with determinants in trace, and just see if I can argue it from that angle too. I think the one that someone suggested is the better argument, but I'm just kind of curious about my original thought. Hmm. Hey, Batatina, or you can call me potato if you want, because you're. Oh, is that the Portuguese word for potato? Welcome in. Hey, you're great back for the second part of the finishing exam. Ooh, good, bad, in the middle. No, I'm just a tutor. Sicario, I've been wanting to, or like that. That's one I've heard of, but I never seen. 7 out of 60. Yeah, that is upwards progress. You know. Okay, you know what? I'm just gonna find it myself. It was good. Okay. I just remember the "It's Always Sunny in Philadelphia" spoof of that, which was really funny. Uh, with fractions or potentially something else. Yeah, I mean, if you want, put the question there, or you can put a screenshot in Discord, and I can try it. It's on Netflix. Okay. Because I'm kind of done paying for streaming services, so I haven't paid for one in a very long time, but it's on my list. Or like it's something that I would like to watch at some point once I figure out how. Can you just like type it in chat? Man, my voice is already not good. Oh, you bought a physical copy? Nice. It's an older book, so hopefully it wasn't too expensive. If the USA is so great, why did they make a USB? Oh my god, Central. That's a very good point. Not enough people are asking that. 22 bucks? Wow. That's crazy good. Saw it on Sunday and you waited this long to send it? Yeah. I admire the dedication. Okay, so 3x times 6y times 1 plus 9w. Do they just want you to simplify it? Or just like multiply things out? Yes? Okay. So there's different orders you can do things here. I think the simplest one, well, let me back up. Well, when you see an expression like this, you normally want to figure out anything inside the parentheses first. But 1 plus 9w, there's not much we can do with that. That's already as simple as we can get it. So I'm going to look outside the parentheses now. So the options are to take this 6y and distribute it inside. But you don't have to call it simple, it's right there, man. Well, it's not simple yet. I'm making it simple. But the issue is then this 3x is still on the outside and things will look kind of weird. So I think my first choice is to multiply the 3x and the 6y. You know, this is all multiplication here, so we can do that multiplication in any order we want. So let's do the first multiplication first. So that becomes 6 times 3 is 18. X times y is just xy. And then we saw times 1 plus 9w. Put a W on the left of the 1? Oh, like, if you want to take a W out of the parentheses, it's not, it doesn't work like that, if that's what you mean. Like, it's not true that this is the same thing as, like, or... This is not valid math here. Like, I would say these are not equal. You can't just take the W out like that. If you want to do that, what you would need to do identifies as equal. You would have to write 1 over W plus 9. And the reason for that is that if we were to look at the original thing and multiply it back out, we would get W times 1 is W, plus W times 9 is 9W, and so that's just 10W. But 10W is definitely not the same thing that we started with, 1 plus 9W. That's why we're not allowed to do it like that. This down here is the proper way of doing it, because if you multiply it back out, 1 times 1 over W is just 1, and then W times 9 is 9W. So that does match the original. I would say I'm not a fan of taking... I'm not a fan of doing this though, because I don't see how it helps us. So I hope that kind of clarifies. How that part of it works. Yeah, the way that I like doing is doing the 6x, or sorry, the 3x times the 6y to get 18xy. And now we can take this 18xy as a unit and multiply it times the 1 and the 9w. So 18xy times 1 is just itself. And then we have a plus there, so plus 9 times 18, I don't know that. It's 81 times 2, 162. 162, I'm running out of space, times wxy. And I'd say this is about as simple, like, that's the most that we can do with this. Depends how you define space, central. The space of my RAM is definitely not infinite. So, Potato, let me know if you have any question about this, but if I don't see anything else from you, I'm going to go back to the problem I was doing before, but if you do ask a question, I'll happily scroll back down. Get here, lambda squared. A plus d lambda plus AD minus BC. Okay, that's... I'm trying to remind myself of this formula here. It's minus. Yeah, my idea for the problem originally was we're doing a plus 2i. What if we look at this and just figured out what adding 2i would cause on this polynomial. This is probably getting a little too stupid though. Yeah, the determinant doesn't cleanly scale with this. That's the issue. I could go back and I could write it like a plus 2 d plus 2 minus bc. No, yeah, I don't really know what you do with that. So I like this argument up here much more. Let's get number 4 also. Um, so they're talking about a equals x lambda x inverse. The columns of that bad boy are linearly independent. Um, does that mean A is invertible? A should definitely be diagonalizable. X should be invertible. Um, A and D, though, are a little bit trickier. You know, this is like a 2x2 matrix. um, I think D is not necessarily true. I think D is false. Because it's not like A and X are somehow they don't have equivalent columns normally. Do they though? Hmm. Actually, What happens if we take the inverse of each side of this equation, I guess? If we use shoes and socks that... this x inverse inverse would go first, but it just becomes x again. Then it'd be lambda inverse, and then this would go last and become x inverse. And I think we know that x inverse exists because of this linear independence piece. Lambda inverse, it should exist because it's a diagonal matrix. Hey, color cone. Can you have... I'm just wondering if like the lambda... I think the only issue is that if lambda was all zeros, but I don't think that's possible, and x is linearly independent. I can't imagine that would be. So I think maybe A is true. The only hole that I can book in this is if we can name a lambda, like if we can name a non-invertible lambda, but does have x invertible. And I'm not sure that's possible. So I might be sending A, B, and C. Yeah. This is 6.2. Is a zero matrix diagonalizable? Not with independent. Linearly independent x. I mean, the eigenvalues would just be 0. So the eigenvectors are just gonna be something weird. Like there's no way they're gonna be independent. It's gonna send every vector to 0. Oh damn, A is wrong. What? I guess it's possible to name that. What kind of lambdas would it be though? I wish it said the actual counterexample. Oh, maybe they would have to be independent for the zero matrix. Hmm. Any diagonal matrix with a zero on the diagonal, give yourself. Well, wait, I was thinking, is this not invertible? I'm pretty sure it is, isn't it? Isn't it self-inverse? Did I do this matrix multiplication wrong in my head? That times that. That does give you 1. That times that gives you 0. No, this is an invertible. Is it not? Because it's symmetric. Well, what about that? Is that possible? No, wait, the one half would need to be there? No? This is invertible, is it not? Am I doing this wrong? Yeah, the debt is non-zero. Okay. So then I'm not sure what you're saying. What then? I think I've given counterexamples to your counterexamples. Okay. The most general mate. Okay, let's look at 7. Can I banish this to the shadow realm? You know what? I'm just gonna. That's a real bit. Banishing to the shadow realm. Um. The matrix will be named A. 1, 1, 1, -1. A, 0, 0, B. Oh, we have to invert that. Can I be a Chad and mentally invert this? I can't be a Chad and mentally invert that. Let me see what's it's got sunned by famished. Let me look at what color cone put first. Hey Jasu. Um it is that right there. Oh, with a 0 in the last spot? Hmm. That will be a counterexample for A. Did you say that and I just missed it? Oh, with a 0 on the diagonal. No, I put only zeros on the diagonal. Okay, no, never mind. I misunderstood what you were saying, I guess. So diagonalizable, but not invertible. Okay, that's fair. Thank you. No, I now that I see the example, I understand exactly what you were saying. I just my mind went to a different place, I guess. And number 4 up here, I thought A was true. It was not, and color code was giving an example of why it's not true. Let's see what Famished put. So this is the exact thing that I was showing you, Famished. These like values that are assigned to each binary digit are these places right here. That's what they mean by that. And yeah, and so that's like by having like a value that like they're talking about like this sort of like conversion thing that I was doing down here. Like that digit right like this one is worth an 8. That's what they're talking about, like a value, because 2 cubed is 8. See, that's important in computer science now, at least some parts. Oh yeah. Um, there are some things in computer science where math is really helpful. Like number theory can give some really like helpful tricks. Having good intuition with just like numbers in general is good for dealing with binary and hex. Oh wait, I should be able to mentally invert this because these have a what's the determinant of this thing? -1, -1, -2. So we divide by the determinant. We've swapped the diagonal, negate the others. And that's our inverse. Wait, is this self inverse? No, it's not. No, it's not. No, it's not. I want to verify this. That times that is 1. That times that is 0. That times that is 0. Times that is 1. Okay, yeah. Machine learning is just math and cryptography. Yeah, but even like more fundamentally than that, like algorithms. If you want to analyze those, that's pretty mathy. Like no matter where you're in computer science, math has some sort of relevance. And I think even the way that you like would analyze a problem involves the same type of analysis you'd use to uh, solve like a math problem. Okay, and so theoretically, we can just do this matrix multiplication, and that's our general matrix A. I guess I'll do the first two times each other. That times that is A. This times that is B. That times that is A. That times that is minus B. That looks like a Q. If you want to find counterexample to some properties of diagonalizable matrix, it's good to start with if the property holds for a diagonal matrix. They're all diagonalizable matrices only differ by a diagonal matrix, only by a base change. A base change? What is? Oh, like a change of bases. My mind was on like the binary and thinking of like number bases, but you're talking about like basis vectors. Um, okay. Change basis given by your eigenvectors. Okay. Everyone's taught by math departments. Uh, I think at least at my university, the dedicated algorithms class was in the computer science department, but I did have to take like a discrete math course that covered some algorithms. But there's also things like I guess like data structures. Um, where am I going with that? I guess like hash tables are pretty mathy. Linked trees, can they be mathy? Maybe not. There's probably a way to get math in there, but I don't know. It's definitely cooked into the base of computer science, though. I like math is. I'd say. Um, that times that. That times that. That times that. This is a weird looking matrix. It's symmetric. Okay. It's my answer for 7. Okay, yeah, I got it right. Fibonacci numbers? What? What is a Fibonacci? The average of the two previous numbers. Huh. The April Fool thing for the Discord LaTeX bot? No. What do they do? Should I make it render something? No, okay, that still works. Maybe it's on like their Discord server. Be funny if they change the arrow slash. Oh, okay. Maybe I won't show that on stream. Slash two slash. Kind of hilarious. I'm not gonna show that on stream. I I don't know if that's the best April Fool's joke to put in your bot, but it is kind of funny. I feel like there'd be some people who wouldn't appreciate that. Hey Jed, Fibonacci is just generalized Fibonacci for any two starting values. Oh, okay. In Metallica, can you demonstrate P times Q premier equals odd number? That two prime numbers multiplied together are odd? Is that what you're asking, Metallica? I assume that they can't be two themselves. Um, so Metallica, I'm gonna. I don't feel like I fully understand the question here, but is this like let me try to rewrite it. P and Q not equal to 2. Prove that P times Q is odd. Is this a fair way to phrase the question? Right. The issue is that 2 is a prime number. Um, so this statement, or it's just not true unless we exclude 2. Yeah, I'm taking this as a translation error, but Premiere is probably prime. Oh, nice. Famished. Oh, that's an angle. I was thinking more like Jed's angle, but that's another angle we can take too. Syntax. Um, but Metallica, I'm still trying to confirm that this is what you're asking. I'm a little bit worried that there's a translation issue and that I'm not, and that I misinterpreted what the question is. Like writing in a notebook, digging deep into topics. Yeah, the act of actually writing something down helps me a lot. Um, I mean, sure, I would take the solution, but I feel like I don't know what the question is, or if, I'm not sure that this is actually the question. Um, yeah, there's a few different arguments that we could make here. Like, we could say that since P and Q are prime, we know that 2 doesn't divide P and 2 doesn't divide Q. So 2 can't divide P times Q. Okay, prime number more than 3. Okay. Two prime numbers. Uh, I'll say like greater than or equal to 3, I guess. So I think one argument can be as short as this. Um, you could also argue that, or you could also say let P, or since P and Q must be odd, let P equal 2K plus 1 and Q equal to L plus 1. So P times Q equals 2K plus 1 times 2L plus 1 4KL plus 2K plus 2L plus 1. And the point of this is that we can factor a 2 out. 2KL plus K plus L plus 1. Oh, true, Jed. And so once you have it in this form, you can say it's an odd number. And Jed is correct. I should specify that K and L are integers. Positive, I guess. Or you can do it mod 2 like Color Code did. Um, yeah, there's a few different ways of saying this Metallica, and I think there's even more than like the 2 that I have on screen plus the one from Color Cone. Um, 2K and 2K prime. Oh yeah, the choice of letter is a preference. Awesome. Thank you for the question. If you have, since I see you're new around here, if you ever have a math question, I'm not around. I like to let people know that I'm not the only one who does this. There's a whole bunch of people who do math help right there, so just know that uh, there's others out there like me too. Yeah, thank you for the question though. Okay, so I did 7. Oh yeah, it's again Gibonacci. I just want to see how they describe it. Do they not describe it? Really? Oh wait. Fourier series? Wait. This isn't Fibonacci. Are Fourier series related to Fibonacci? Oh, no. This is a different thing. Okay, I was like, if Fourier series are relative to Fibonacci, my mind's about to be blown. This is a different aside, though. I'd much rather just scroll through this nearly 600-page PDF until I find it. uh, really? Apparently, it doesn't support searching. That's annoying. Just an index, I guess. You can do it the old-fashioned way. Gibonacci. Gibbo. Really? Is it under F for Fibonacci? It sure isn't. All right. The man doesn't want us to know about Gibonacci. In this case, the man is straying. Thank you for the follow, Metallica. Wait, 25 factorial? Oh no, you wait. Oh, you're about to say because of the other alert? I wish I was high on 25. Okay, 11. If the eigenvalues are 2, 2, and 5, the matrix is certainly... It should be not diagonalizable, right? If you have a repeated eigenvalue? Is that how that works? Yeah, right? Maybe? It should be not diagonalizable, I feel like. I have a bachelor's in applied math. And I'm probably one of the least qualified people out of that list of streamers. um, I know I just am the least qualified. I'm gonna start in a master's in the fall, hopefully. Well, I will be. Um, yeah, that's my level. I have a minor in computer science as well. Ratio of women to men in Helsinki mass is like 25% women. Damn. I wonder what program has the worst ratio. Honestly, I bet that's probably about average. I was trying to think of what my graduating class was like, but there were literally 4 people in it. And the university overall was like 60% women, 40% men. So it's not really a good not really a good example. Did math in Australia was in the 90s? Dang. Oh wait, no. You did you when you did math in Australia in the 90s, it was lower. I think like it was like 90% men, but it might also be 90% men. For Unity case, they're about 50-50. Really? I want to see, is there like an article about this? Ratio of men to women in universe. I mean, maybe I'll say in math by country. That might be too specific. There could be a study of that, but this is just saying general. Oh wait, let's see what's on this page. Sardoche. That sounds familiar. Isn't that a super big channel? I feel like I've heard the name. I think there are more than 90% men just based on my recollection. Yeah, I don't know. You guys, you're the only one in the room in the later years. All one went to stats. Oh. Yeah, I don't really I think my class like, two guys and two girls, but that's not really it's not a very big sample. Um Interesting. A lot of drama, and he's very good at maths. Oh, really? Oh, thank you, Jed. Let's look at that. I'll have to look. Does he actually do streams about math? Sure, it's necessarily readable. Oh, hey, yeah, this is basically what I wanted. Oh, frickin' Iceland. Just no one likes math in Iceland. Oh wait, no. There's 0 women. I thought this was like men on one side. Actually, it wouldn't make sense to have men on one axis, women on the other. Portugal's is doing good. Wait, so why are they plotting percentage of women in math? So someone who is on the left side but high up would have improved a lot. People who are about on the y equals x are about the same from one year to the next. That's how we interpret this. So people who actually improved are the ones like above that diagonal. No one got significantly worse. Like France got a tiny bit worse, it looks like. What's the actual scale? Like Portugal's at above 45. A lot of them are just hanging out from 5 to 15% though. This is women mathematicians for some definition of mathematician. Does that mean studying math or publishing papers? I'm not sure. Women full professors. The percentage get even lower now. The top of the scale is 35. Portugal is just kind of crushing it. Here's the maps. Huh. It's kind of interesting. The more north, it's not that strong of a correlation, but the farther north you get, the worse they do. Hmm. Like, what is that? Estonia? Are they the trend breakers? It's probably Estonia. I know it's Estonia, Lithuania, and Latvia. Those three Baltic countries. I don't remember what order they come in though. If you want textbook is designing programs and other technical stuff, but some Java, Python, C++. Like all three of those? That's kind of surprising. Normally, if you're first learning, you just kind of stick to one. Do one of those name the countries in Europe? Honestly, that could be funny. Let me find one. Europe country quiz. Countries of Europe map quiz. Sporkle. This looks like what we want. You like this chart, you blame taxes. Math rankings by country 2025. It's just the number of mathematicians, though? This probably is... You want a percent of the population, though, do you not? Oh, I see the joke, though, Jed. Like, we need to be... Americans have to be good at math because of our tax system. That's kind of true. That... In top 20... I wonder what exactly their definition is. But like America, like by whatever this measure is, America is crushing it. But this seems like a really specific measure. The top 2755 mathematicians in the world and where they are. Oh. How are they saying the top ones? Like the most published ones? It's probably something like that. By like number of publications. Yeah, and citations, I guess. So I guess the most published / the most cited mathematicians. France and Germany are the country with the most mathematicians. Yeah, I mean, I wouldn't be surprised. Just it kind of depends how you define mathematician, though, I guess. Wait, what is this other link that I have open? I somehow got an Amazon page pop up. Sorry. Yeah, this is a really specific like ranking. I wouldn't really like like America is the best at math. Oh. Okay. Jeff Bezos wants my credit card. Yeah, he sure does. Wait, what country am I entering? Is it highlighting one of them? Am I stupid? Well, yeah, but like, is it like, do I just say the name of a country? Oh, no, I should have to point to them. Oh, I want to do the reverse, where it shows me the shape and I name the country. I could do this too, I guess. This is going to be a lot harder. Or, actually, no, I'm sorry. I was hoping for they would name the country and I'd point to it, I guess. I could do this version of it too. Germany, United Kingdom, the Netherlands. How the hell do you spell Liechtenstein? Liechtenstein. How do you? They need to get an easier to spell name. C++ used for game dev? It can be. Switzerland. Okay. Let's get Maxi. I assume that Jed found like a similar thing. Because it like there'll be somewhere I know what the country is, but I don't know how to spell them, like Liechtenstein. Like, that's like the same thing. I kind of like the way the site looks though. Wait, okay, Latvia. Well, the top one there is Estonia. We established that with the mathematician thing, right? So it's one of these two. uh, ooh, Latvia. I think. Oh man, do they spell eel? E-E-L? I feel like I would remember that if they did spell eel. It might be E-L-E. There's a timer. Oh, it's counting down? Oh my god, we have to speedrun it. Belarus, that. Luxembourg. Oh, you're that little guy, aren't you? Greece. Oh my god, dude. Moldova. Moldova's tiny. That's right, and it's by Croatia, and Croatia's a big C. Is this Moldova? Oh frick! Never mind. I should have known it was over there. I'm from America. Montenegro. Right, I don't remember. There? Nope, it sure isn't. Sweden? Denmark? Belgium? Okay. Vatican City, north or south? South? Okay. North Macedonia? That one? Nope. There's no South Macedonia. Lithuania? Oh my god. Austria. Fuck! What is that country there? Okay, yeah, I'll figure it out later. Bulgaria. Are you Bulgaria? Nope. The Balkans are unfair, okay? Albania? Albania is definitely right there. Hey, I actually got one. Ukraine right there. Monaco. You're probably the other tiny one? I don't know. Nope. France. Slovakia. Nope. You're up there. Really? Slovakia's up there? Hungary. Oh, was that Hungary? No. Bosnia and Herzegovina. Are you right there? Nope. You. Oh my, dude. I didn't think I'd do this badly. Romania. Romania. That has to be Romania, right? It's right by Moldova. Okay, good. Poland, right there. Estonia, right there. UK, right there. Serbia. Wait, what country is... It should be the... Trying to think. That one? Oh my god, I got it right. Switzerland, that should be you. Andorra. You're probably there? I don't know. Nope. Cyprus. Kosovo. Oh, you are a small boy. Are you right there? You are. Slovenia. Probably that one. I have no clue. Czechia. Is that what this is? It is, okay. Spain, Turkey, Ireland, Liechtenstein, my arch nemesis. You're probably that one. Nope. Wait. What? Okay. Oh my god, that's the Netherlands, dude. I'm freaking... No, I just got tilted. I did. Oh my god. Ugh. Malta. Who knows where Malta is? Is that Malta? Did I already click on that? I guess not. San Marino? I don't know. I need to zoom in. Why does Russia not feel inclined? That's a good question, Maxi. Yeah. I can't even find. Uh, okay, sure. Norway, 74%. I feel like some people I feel like there's a lot of Americans who do way worse on that. Okay, the one I keep. Okay, yeah. Do Africa next. No, Georgia, Armenia, Azerbaijan. Oh, are they? They're like right there, right? What? I don't know what continent they're considered a part of. Uh, Czechia. Oh, yeah. I did I say Czechia by accident? We're gaming. Yeah, we right. Do Africa. No, Africa has a lot of tiny ones. I did have to memorize every country in the world. I think in like 10th grade or something. We did it in like continents. But at one point I actually like knew these. We'd have to know the tiny ones. We didn't have to like Andorra or Monaco. Yeah, Max was saying like that little piece should be marked as Russian, but it's for whatever reason not. Do you expect to reinvite your guys? That's a good thing to ask. Hey, comments. Um, for does have many tiny ones as Europe? We can do an Africa one. We don't have a question in queue anyway. I corrected Czechia backwards. Wait, Monaco? It's not. I've heard people say Monaco though. I don't know. My takeaway was the wrong one. I don't. Czechia. Oh, okay, Czechia. I see it now. Behind ads. Okay. Does the same site have an Africa quiz? Let me see. I don't know why I'm hiding it. Let me just show it. Find the country of Africa. Monaco. Oh, Monaco. Mo Monaco. That's where I've heard it. Monaco. That sounds. I thought people called it Monaco. I don't know. Kenya. Kenya should be. No. Wait. Uh, Ethiopia's right. It's one of these two, and Kenya's right next to it. I think that's Ethiopia. So this is Kenya. Fuck. Madagascar. That one I know. I played Risk. Say, oh, fuck if I know. Okay, Zimbabwe. You're somewhere in the bottom part. Oh, Ethiopia must see that one. But wait, this no. I don't know. Freaking I don't. Okay, that's Zimbabwe. Algeria. You're that one. No. France. Where would France have colonized? Are you that one? No. Or you're over here. Isn't it? That's Morocco. Is Algeria one of these? That one. Okay. That was mostly a guess. Libya. I don't remember this. Libya. That one. Nope. Ethiopia. Please tell me you're that one. Okay. Botswana. That one. Nope. Mauritania. That sounds like an island. Nope, it's not. Democratic Republic of the Congo. That's one of. Are you that one? I feel like you're that one. Okay, you are. Okay, that's probably by Mauritania. No, okay, it's completely in the opposite corner. Uganda. You that one. Maybe you're that one. Where is Knuckles from? There? Nope, it's right there. South Africa. Burundi. Ooh, they grow coffee too. Burundi. It's by Rwanda. Rwanda's one of those small ones, I think. Damn, I guessed the wrong one. Namibia. Ooh, 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 ooh. Somewhere in the south. Are you that one? Nope, it's that one. South Sudan. Okay. Gabon, no clue. You're clearly there. No, oh, I almost guessed right. Ghana, ooh. Ooh, 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 ooh. That one? Yeah, okay. Rwanda should be the other one. Morocco is that one. Senegal. That's Somalia, I think. I don't really know. Nope. Wrong coast. Tunisia. I've heard of that from Call of Duty. Djibouti. Maybe the best name for a country. I don't know where it actually is. I'm gonna guess there. Nope, Djibouti's over there. My what? The Gambia. Um, the Facebook, the Google. The Gambia. I don't really know. Nope, it's over there. Burkina Faso. That's an island, isn't it? That sounds like an island. Maybe it's probably not. I'm gonna get boned here. It's not. Guinea-Bissau. Nope. Mali. Oh, the Azores? Okay. Mali. That one? Nope. Dude, I don't know any of the countries in this part of Africa. I keep guessing things over here because I feel more familiar with it. But even then, I'm not. Liberia. That one. Nope. Central African Republic. Okay, well, I'm gonna guess that's somewhere in the center of Africa. Uh, okay. Egypt, I know that one. Guinea. And I guess it's right next to Guinea-Bissau. Okay. However you pronounce that, that has to be an island. I refuse to believe that's... Okay, it is an island, just not the right one. Mozambique. Okay, I got that right. Benin. I have no clue. Tiny one. Nope, that tiny one. Malawi. It's that tiny one. No, it's not. Cabo Verde. Green Cape? Isn't this the Cape of Africa, this region? I don't remember. I'm gonna guess that. Nope. So, ah, Republic of the Congo, not the Democratic Republic of Congo. I didn't realize these were two separate countries. I'm gonna be honest. Bam. Okay. Cameroon. Oh, I've heard of this one. I don't know. I don't know where it is. People vacation there, right? I'm gonna guess there. Nope. Lesotho. I have no clue. I never heard of that one. You're there. No, you're there. Togo. They make sandwiches there, I think. There? Nope, it's there. Comoros. Dude, this is terrible. I never heard of this one either. I'm gonna keep guessing this one until I get it. Nope. Oh, where are you? Yeah, I think you're there? Nope, you're there. Eritrea. That's an island. Togo was famous for their chilies. Sandwiches to go. Wait, Eritrea, is that not an island? I don't see any other islands that are up for grabs. Sure, there's always news articles about them, right? Eritrea, I'm gonna say Is it the one that I've always been guessing? Nope, it's over there. Sudan. It should be north of South Sudan. Ivory Coast, I'm gonna guess. I don't know if it really helps me. You're that one. Nope. Sierra Leone. I think you're there. No, you're there. Oh, that's what I was guessing. Angola. Oh, it's down there. Somalia. Tanzania. Nope. Equatorial Guinea. Got that right. Chad. What a Chad. Oh, it's up there? Okay. I didn't even see that one down, that spot down there. That's Zambia. Okay, terrible score. Yeah, we should do some actual math, but average score is 66%. If at first you don't succeed, destroy all evidence that you tried. Ugh. There's no way the average person gets 66% of these. I call bullshit. People are studying. Anyway, that was so funny. We started by looking at, like, the percentage of women mathematicians in each country, and we ended by doing geography quizzes. Determine expected value on this given random guesses. Wasn't that just if you have 54 total countries, or whatever it was, 57, isn't it the sum from 1 to 57 of 1 over n? Right? Oh, wait. No, never mind. This isn't. Like, I think that's all it will be, the expected value. .62. So if I did this right, you could expect to get 4 or 5 countries right by complete randomness. If there are 57, I already forgot the exact number. No? Well, you know, do tell Jasu. That seems like about right for expected value to me, at least. Yeah, so that, like, your first choice, you know, we're just pretending there's 57 countries. You have a 157 chance in your first choice. Then a 156, 55, all the way up to the last one you should hopefully get right. But yeah, that's what this is doing. So God bless Wolfram Alpha calculating that, like, basically by hand. Yeah, I think that's okay. Decreases. But yeah, it's all commutative. Okay, I think for 11, I was saying not diagonalizable. You replace sigma with big pi, that would be the chance of getting them all right. Yeah, I think so. Yeah. We could look at that. So you have them all right by complete luck. Wow, that's a small chance. You would have a decimal, what, 76 zeros in a 2? I didn't even be that small. I guess it makes sense. If the only eigenvectors of A are multiples of 1 and 4, then A has... a repeated eigenvalue, certainly. The inverse thing, I think, may or may not be true. I think B and C are the true ones. And then for 11, only C. Basically just sorting the countries and getting them all right. It's probably picking the right order. Oh, for this book, this is Introduction to Linear Algebra. And this is just introducing like eigenvalues and eigenvectors. So we're just talking about matrices here. This is the book. I think just Rn. I mean, it should be true for any size of R, but like R2 is fine to think about, I think. Oh, I guess, sorry, for 12, yeah, I guess it's R2. They haven't got into complex numbers. Well, only a tiny bit for like a complex eigenvalue or eigenvector, but let's just see. I want to check the answers anyway. Yeah, like 1/4 is valid vector space, but I mean, we can talk about the. I'm pretty sure we can say these two things are true. (11 and 12). Wait, for 11, what did I say? I said only C is true. What? Did I get it? What? True, no zero eigenvalues. Oh! Yeah! Okay, that's fair. It's not diagonalizable. Right. Repeated lambda may have a full set of eigenvectors. Wait. What the fuck? It's certainly diagonalizable and it's certainly not diagonalizable? Wait, how are these both false? Wait, what? These can't both be false. It can't. What would have to be false? Would it have to be true, just logically? How are these both false? It's not sufficient to say either. Oh. Okay, fair. I guess, yeah, certainly. Okay. It may or may not have the full set of eigenvectors if it's repeated. Okay. That's a counterexample for C. Hey, Phobos. Bonjour. Um, 225. Okay, yeah, fair enough. You hate that Twitch makes that into an emote? You rather just have the frowny face? I have run into the annoying thing. Oh wait, you know what? I don't want to accidentally show the dick on Twitch. I'm gonna delete your your that message. Um, and I'm not talking about my dick. Um, the Discord LaTeX bot has an April Fool's joke, and I don't want to. It's not an actual dick either. It's just a funny drawing of one. Anyway, um, I run into that Maxi with like B colon or like B, yeah, like B like that. Twitch turns that into a face if you remove the space. F of X, sorry. Jordan Form is a good source of matrices that are not diagonalizable. Okay. What am I looking at? I'm back here. Um, if the only eigenvectors of A are multiples, okay, so let me think again about 12. If the only eigenvectors of A are multiples of 1 and 4, I was saying B and C must be true. Yes. Okay, so X inverse can't exist because the columns of X aren't independent. Backwards B. There you go, Maxi. Um, the repeated eigenvalue. Oh man, does that have to be true? Maybe it doesn't. No, I think it does. It has to. It can't scale the same vector two different ways. For 12, A can literally be the identity function if you pick the right vector space. Um, I'm gonna say the I think I'm sticking to my guns. I think A is false because it could or could not have an inverse. But B and C are both true. 12, false. We don't know if lambda equals 0 or not. Good. Eigenvector is missing, which we only have them for repeated eigenvalue. We know there's only one line of eigen. Okay. I need to remember that the product of the eigenvalues is equal to the determinant. That's a property, right? And the sum is equal to the trace. I believe that's it. I guess I can look. Something about whether eigenvalues can be complex. Is it the eigenvectors that are complex then? Or I'm thinking like they talk about like the rotation matrix as having complex something. Okay, yeah. Product of the eigenvalues is a determinant. The sum is the trace. Oh, the eigenvectors are complex. No, okay, they're both complex. Oh, but I see where we're going with the 3x3 color cone, where like for a 3x3, you either have 0 complex eigenvalues or 2 complex eigenvalues. For a matrix of real numbers, you can only have 0 or 2 complex eigenvalues. I assume that's what you're saying? Or that's where you were like going with that? Completes matrices that determinant is 25. Let's bring 13 in. We wouldn't have repeated eigenvalues in that case. Yeah, yeah, we wouldn't be able to have them. Interesting. So that first one, we have 16. So the other two entries need to multiply to -7. No, 9. Ah, I don't know how math works, dude. It's 9. So we need a -16, I hope. This is just the reverse of the problem of the arithmetic I just messed up. So a -4. And this one, there's multiple options. I'm just choosing that one. This one, there's only one option. This one, there should only be one option. 10, 5, -5. This is already going to give us a positive 25. So really the only choice here is 0. The trace is 10 for all of these. Oh, hey, okay, look at that, yeah. Okay, yeah, so they're saying if the determinant is 5 and the trace is 10, then we know already the characteristic polynomial is lambda squared minus 10 lambda plus 5. And that is lambda minus 5 squared. Find an eigenvector with ax equals 5x. Do they, is the point is that they're all going to be the same eigenvectors? I assume. Did I do a dumb? Oh yeah, I did a big dumb. Sorry. Yeah. The determinant is 25. I was looking at this line of text. Like, oh, 5. But no, the determinant goes in that spot. We engineered the determinant to be 25. And I guess we just had to find the eigenvectors the old-fashioned way. I'm also curious if the eigenvectors for this one are going to be the same as if we did like 3 and 3 or something. Or 3 and -3, rather. Anyway, 8 minus 5 is 3. -9, 1, -3. The eigenvector, we're solving v is equal to 0. Like this, probably. X1 is equal to 3x2. So then we can say that, I think it's Kasai that we use. And Kasai, is that Kasai? Or, no, wait. What? Wait, what the? No. Yeah, I think I got Kit Kasai, right? Oh, you know what I can do? I can do I have this command set up still? I do. Oh, I got it backwards. It's that bad boy. Worst. It's the worst Greek letter. Easily. If x1 is 1, or x2 is 1, you do some marking after Easter. Is Easter on this Sunday? I don't even know. No? When is Easter? Oh, it's on 420. It's funny. Why do you know you're gonna need to do marking like that far in advance? Greek or oh, I guess I was thinking of everyone else's. So will all the others have the same? Is the point is that these are all going to have the same eigenvectors? Let's try it with the second matrix. So we're taking that matrix, we're subtracting 5 off the diagonal. 4, 4, -4, -4. These are not going to be the same. Whatchamacallits. I remember having to get so many eigenvectors with complex numbers, and doing this procedure here with complex numbers is a million times more painful. Well, I don't really get. I guess they're just making you kind of do things here. I've done this part of eigenvectors a million times, so I don't really care about. I thought there was gonna be some bigger point for 13, but I don't really see it. Did I make an oopsie? I didn't get that for the first one. Wait. 8 minus 9, 1, 2. Eight minus 9, 1, 2. This is diagonalized. Wait, what? No, it's not. No, it's not. No, it's not. No, it's not. That's a different thing. I think, what? I did this right. If the determinant and trace are the same for two 2x2 matrices, they are equivalent. Trace 10, determinant 25. 9, 4, minus 4, 1. I feel like I just got the opposite of that result caller. It seemed like that was the point of this, but I think the matrix I named doesn't seem to work. 9, 4, minus 4. Oh, minus 9 goes down there. Trace 10, determinant 25. Same eigenvalue, different eigenvector. With my matrix here, trace 10, determinant 25. Eigenvalue same, different eigenvector. Was I... Did I misunderstand? Is there another condition here that I'm missing? Welcome to 5105. Oh, is that the... what the Jordan decomposition thing is doing up here? No? I saw the same matrix there. My concern is that this matrix that I named here, I was supposed to get eigenvectors of the form C minus C. But I feel that I've named a matrix that meets all the qualifications, at least of the problem, and I get a different eigenvector. It has the right trace, it has the right determinant, it has the right eigenvalue. But it does not have the right eigenvector for some reason. So I don't know. I apparently didn't make the choice the book intended me. They were intending for that choice with 3 and minus 3. I did 1 and minus 9. But I don't see what's wrong with my choice either. Your matrix are written in different bases, so your eigenvector will look different in other bases. I mean, it's kind of weird that like we haven't even gotten to like linear transformations yet. I don't know that. Like I seen them before in like the linear algebra class that I took. I don't know. I don't remember that much about them. Like I haven't gotten. I've only gotten like through chapter 6 in like the YouTube like lectures that the author of this book did. Well, he's kind of pulled some random things from later on from the applications pieces, but I don't know. Well, the rank of a minus 3i is 1. Wait, does that? Why does that matter though? I want to think about number 14. So I know that the rank is 1, but then you know, like when they're teaching matrices before linear transformations, we sort of lost the entire geometric intuition, only crunching numbers. Yeah, I'm kind of wishy-washy on how much I even like this book in the first place. I just wanted something that was gentle enough to help me remember the linear algebra that I've already learned. I picked up some nice things from it, but it at least for a little bit that I've done from it, it hasn't been my favorite. I don't have a favorite linear algebra book. I guess it's the one that I've actually like tried to read, but that's bad. If it's the only one I've read it and it's still not my favorite. um, what do we learn before from the other problem from number 3? If you add or subtract from the identity, it's the same as, or if you take a matrix and add or subtract off the identity, it's the same as, or the eigenvectors remain the same, only the eigenvalues change by the same amount. Um, I just need to see what goes wrong here. Oh yeah, we're gonna get, I guess, only 0 for the eigenvalues. Thank you, color cone. Um, See, we only get 0 for the eigenvalues. But if there is a repeated eigenvalue, how to get the other eigenvector? That's one thing that I forgot. You have to do some weird thing. Um, I think that's what they're called. But like, just because you have a repeated eigenvalue doesn't mean, or like, if you have repeated eigenvalue, you still may or may not have, n many eigenvectors. And if you do have a repeated, I forget how you would check. Or if you have a repeated eigenvalue, I forget how you would check for the eigenvectors. Kernel of a minus lambda I squared. Really? I guess you need an X there, right? Dimension of kernel a minus lambda I doesn't agree with the algebraic multiplicity. You get in trouble when the matrix is not diagonalizable. The dimension of the kernel doesn't agree with the algebraic multiplicity. Really? So if you have, let's just say we're working in like with 3x3 matrices. The kernel, okay, wait, kernel a minus lambda is your eigenspace spanned by your eigenvectors, whose eigenvalue is lambda. Okay, right. I'm still not sure where the a minus lambda I squared thing comes into play, but um yeah, I guess I'm asking like, well, oh, where it would come from, I guess, is you would need when you're getting your eigenvectors. That I remember now. I think it's like your augmented matrix, like I was doing before. You would need something like just to make things up, like 1, 2, 3, 0, 0, 0, 0. Like you would end up with something like this, I think. And this is where you get two different eigenvectors from one eigenvalue. And I'm sure there's a better way of saying that, which is what you're getting at, color cone. Or is it this? Or do I need to put something in these two entries? No, I think it's like this. You would say like 1, 0, A plus, well, not. Minus 2A, A, 0, B, minus 3B, something like that. I don't remember. I think that, well, my mind might have just been wandering. Uh, with how you would actually get the other. If you do have repeated eigenvalues, but every possible eigenvector, how do you actually find the eigenvector? I think that's where my mind had wandered. And I think the answer to my question is that at some point down the road, when finding the eigenvectors, you would end up with a matrix that looks like that with two different free variables. And if you don't get that, then you're in trouble. And you can't diagonalize. Okay. I think that's what I was trying to figure out at least. I don't think it was relevant to number 14. Or if it was, I don't remember how. Oh, this is a Jordan form type of matrix, isn't it? No, I mean, we haven't like learned that in the book, but uh I'm still trying to figure out why the first sentence is true though. Why does the rank being 1 mean that it's not diagonalizable? They have to the entries the eigenvector or the eigenvalues need to add to 6 and multiply to 9. So it's just 3 repeated. Or the eigenvalue, there's only one eigenvalue, and that's 3 with multiplicity 2. Um, and we only get one eigenvector when we try to do a minus lambda I. If a is diagonalizable, it means that it has, or if a is n by n, then if it's diagonalizable, it needs to have n many eigenvectors. Do you agree with the case? In the case there is one eigenvalue, lambda, the space of the eigenvector is kernel a minus 3i. Yeah. Yeah. Or yeah, I was mentioning that 3 is the eigenvalue, but if that is dimension 1, we're in trouble. Oh, okay. We need to be okay, yeah, we need to have the dimension 2. Yes, it means not 1 by 1. In this case, we need to have dimension 2. Um, okay. And yeah, we get like from this matrix that's only dimension 1 because oops, we only just get the one eigenvector, like 1 and then any. Well, wait. Never mind. I don't know what I'm saying with that. It's 0 and then any number. Yeah. Okay. That's Sigma hope is the Jordan form. If we like to calculate it, we would need generalized eigenvectors. Okay. Change one entry to make a diagonalizable. I assume, could we change any entry? No. We would not be able to change the 1. No matter what, uh, there's no way we can change that 1 to make it diagonalizable. Everything else, I bet we could. Because if we change either of the diagonals, either of the diagonal entries, wait, oh, change 1 for 0. Ah, it's basically the identity then. And the identity matrix is diagonalizable even if it's a boring one, right? Well, okay, yeah, sure. Like this should diagonalize as like the identity, right? I'm just kind of guessing. Oh yeah, no, it has to be this. Duh. Okay, sure. I guess we can change the 1. um, the thing I was wondering about is that if we do the same argument as in the first sentence, and we do 3, like we do this matrix minus 3i, we just get the 0 matrix. And that's definitely not rank 2. Here what hurts us is that A is already in Jordan form. Jordan form is not a diagonal matrix. I'm never sure that A is not diagonalizable. Change by A in such a way that characteristic polynomial no longer repeated. Yeah, like I think either of the threes we could change to almost anything, or maybe just anything besides three. Well, zero. Zero might be an issue. Because that's gonna zero out. Is it maybe no, it might not be an issue. I guess I'm gonna try it. I still don't I there's still something I'm not connecting about this argument because I don't get how the argument applies to this case with well it is diagonalizable. Is that the rank of this thing isn't 2 though. So I don't know. I guess I'm gonna look into if 0 actually works. um Dimension of the kernel, not the rank. Those are different things. Oh, okay. Yeah, sure. The dimension of the kernel would be 2. So wait, then what was I then how did I misuse maybe I didn't understand the original argument of that like I thought I did. If the rank of a minus 3i is 1, then the dimension of the kernel is 1, and that's the important piece. Okay, that's what I needed to I should have realized that the rank and dimension of the kernel aren't the exact same. You have to do n minus r. Okay. Okay, so 0 is okay. It should be it should be diagonalizable because we're getting distinct eigenvalues. Okay, so the threes, as long as we change them to not be like either one of them, we could change to just not be 3 and we'd be in business. The 1 we can change to a 0. Let's write this down. The 0 we need to investigate still. Can change the 1 to 0. You are technically correct. The best kind of correct. Now the 0. The 0 would change our determinant, but not the trace. I bet we could change it to anything that's not 0 and be in business. Thank you. Um, if we changed it to be 1, We should be okay. Let's confirm it, I guess. One is potentially a risky choice because it matches the one over there, but I'm a risky person, apparently. Lambda squared minus 6 lambda plus 9 minus 1. Okay, it's going to be some stupid roots for this. But oh no, it's not. It's not stupid. Okay, cool. Yeah, I think we can change the 0 to anything else. We're not... There's not a trap here where there's some random number where it's not going to work, right? I don't think so. I think it's only 0. Yeah. The only thing that matters is that we don't get a perfect square. Yeah, exactly. And so 0 is the only thing that does that. So Strang didn't even say that you can change the 1 into a 0. You don't have any choice for the 1, but the 0 would work. Just saying that you didn't say that. Dude, I was just taught to how to get the eigenvectors and eigenvalues. I like my classes never ask questions like this. It's kind of it's kind of good to or I'm enjoying seeing this side of linear algebra. Um, the powers of matrices, I don't care too much about. I feel like I understand the basic fact of like this diagonalization being helpful for taking powers of B in that case. I mean, I was thinking in my original classes, like I did watch like the lecture that he did probably I watched like a month or two ago by now, but I was mostly just taught this in regards to like differential equations. I don't think my actual linear algebra class got into eigenvalues. I think it was mostly just about like vector spaces and doing it like changes of basis. Recommended. If lambda equals 0, then x is in the null space. Okay, let's bring this one in. If lambda equals 0, x is in the null space. Sure. If lambda isn't 0, then x is in the column space. Yeah, should have to be. Those spaces have dimensions n minus r plus r equals n. Uh, I did say it's like some linear algebra was recommended for the general relativity. I was kind of just spitballing with it. But for the stuff with tensors, I think they rely on a lot of linear algebra concepts. That's why I said that, at least. Um, I don't know if we're gonna need that much linear algebra since we're not gonna be able to get that far in the book. But I think it's somewhat helpful, as far as I know. The class you're taking for dynamical systems are spending half their time computing exponential of a matrix using either diagonalization or Jordan normal form. Oh, nice. Okay. I do really like dynamical systems. Hey, Dessen. F maps V to W, G maps W to V. If is that composition F of G is bijective? What's the null space of G in the image of F? Uh, oh God. Where's that F times G? The null space of G is 0. The image of F is W? Shouldn't the image of F piece just be from the definition? Like, isn't just W the image of F? Oh, well, hmm. Is this saying, are V and W basically the same space? If it's one to one and onto. Is the point of this that V equals W, I guess? Can consider the inclusion of R and R2 as your F. Take G to be the projection from R2 to R as your G. Maybe they don't equal, yeah, it's just equal dimension. Hmm. I still don't, or does it even matter? I still don't quite know if that's composition or multiplication, but I it it's just like so it's just like such a general question that's hard. I don't know. Girish, what level of mathematics does this question represent? Uh, I guess this is linear algebra. Uh, it's kind of abstracted though. Like maybe you wouldn't be thinking about questions like this in your first like semester of it. I don't exactly know what you call this question, but it's something like university like undergrad, all right, like university undergrad level. If that's more helpful. Its composition otherwise being WFD one dimensional. Might it just be the same? Or I mean, I was imagining that V and W could be like matrices, I guess. But okay, if it's composition, I was kind of leaning towards it being composition anyway. But I don't know. F of G is bijective. Hey, wait. I mean, wait. What am I thinking? No, I don't know what I'm thinking. Um, no, I don't think I know how to do this. So unless someone else can answer it, I don't know. I'm just kind of confused. I mean, I don't know what to sketch though. Like, I f of G would send V back to V, or no, f of G. You would give G a W. G would send it to V. F would send it. Okay, so it would send W to W, f of G. I don't know how you use the fact that that's a bijection to say anything about those though. G has to be injective. I guess so, yeah. It injective is the same thing as onto, right? I always get the terms mixed up. No, injective is 1-to-1? Okay. Isn't being onto more important? If she already killed some vector to 0. But that's why I thought onto is the important one. You need to assign to every element of V to have a chance at getting back, right? Wait. Does FG... Do I have these backwards? Is FG F of G of whatever input or G of F? Like, isn't it reversed? Like, one that goes first is the inside one for some reason? Oh, for Pinbox? Okay. Like, I think the inside one should be surjective. That, but evidently not. Being very Canadian. Sorry. Um, I woke up the A on your iPad, really? Oh, like Siri? Yeah. How the kernel looks geometrically? I mean, I know it's the things that get sent to 0. I don't know how you draw that. I can't find the right thing to Google. I I have no clue why the injectivity part is more important, but I just listened to the collar cone there because I have no clue for myself. I'm going back to note 26. Lambda equals 0x in the null space, then it doesn't equal 0x in the column space. Wait, the null space and the column space don't usually have the same dimension. They definitely can't both be n. I don't get what this is saying. Or maybe these are different situations depending on lambda. I don't want to say. I think I just had my like brain crash. I can't just like think about this anymore. Um, Destin, if you got the help that you need, then I'm glad because I think I'm just gonna call the stream. To be honest, jumping jacks. This is gonna be a workout stream. I haven't watched them for a little while. I've watched them. I'm past the halfway mark. I took a pause so I could work on some of the exercises from the chapter, like from these like first six chapters. Yeah, I mean they're definitely not flawless. Like there's something you said that I really don't like. Um, but in general, I really like them. I'm probably gonna try and like plow through the rest of them. 0 to x to y to z to 0. I don't know, but I don't have the brain power to think about it. Um, I think I'm gonna call a stream here, guys. So, and if anyone's here on YouTube, thanks for being here. I'm going to be back on YouTube on Thursday.